Okay, so we were discussing computer arithmetic, and under the topic of computer arithmetic, in the last class we discussed about division operation. So all the division operation started from the last class where we introduced the restoring unsigned division initially. This algorithm is about if you go wrong in your trial subtraction, then you restore that result to its previous value. Then we had a non-restoring unsigned division algorithm plus a non-restoring signed division algorithm. And that was the only signed division algorithm that we looked at, because in any case, if you go for SRT division as well, there is always a complicated correction step at the last, and we saw why we can end up in that case where our quotient and remainder needs correction. This is because in division, the trial subtraction is one thing, but it might happen that if you're talking about signed numbers, then it might happen that your result satisfies the main conditions, but then there was an additional condition for signed numbers, and that is that the sign of remainder should match the sign of dividend. And if that is not the case, then you need a correction step, right? So we looked at a single non-restoring sign division algorithm and the hardware for that. So today we are going to look at floating point and floating point arithmetic. Right. So before I go to floating point numbers, I would like to have some response from you. So only two of the students are here. Ms. Shirina, I know she is a student of NAD. Mohammad Fahad Khan. Have you ever studied floating point number systems before in your undergraduate?
No, sir, I have an idea about it, but not in the specific detail.
Okay. Okay. Secondly, I would like to say that I'm recording this from another room because that is not available right now. So if is my audio quality fine? Because previously I didn't have the fan open, but this time it's the fan's voice as well. So is it audible?
Yes, sir, it's clear enough. We can understand you as well.
Okay, that's good. That's good. Okay, so let's start floating point number systems. So for those who haven't done floating point number systems, I'll start from the initial, and then we are going to come to the arithmetic for floating point numbers. Right, so the idea here is to store numbers, real numbers, right? So we talked about integers, and there were different encoding formats for that. We have signed magnitude number systems that can store positive and negative integers. We have a 2's complement number system and different other number systems, and they are applicable. So 2's complement is the one which is more applicable in computers, and but these are all for integers. Okay, Mohammed Imtiaz has also joined, but these are also for these are only for integer numbers. So when you come for real numbers, how do you store a real number? That's the question. And we looked at a few of these previously as well when we were looking at the encoding schemes in our very initial classes. So I'll just go through that once more. Fixed point number system. So when you talk about fixed point number system, you have those bits. For example, in the case of computer arithmetic, you're always going to have some fixed size for storing a number. So for example, if you have got 16 bits or maybe 32 bits to store a number, you are going to reserve some of the bits for the integer part and some of the bits for the fractional part, which is mentioned over here. If you look over here, then we see here that there is plus minus w point f, which is representing a plus minus means that you need a bit as well for storing the sign of that number. Plus you need some bits for storing the integer part, where w is representing the integer part and f is representing the fractional part. The decimal point is fixed. That is, for example, if we are talking about um, if we are talking about a number like this, for example, if you have got say 5 bits, so of those 5 bits, say for example, if we have got 5 bits, so of those 5 bits, 1 bit should be reserved for the sign, and then okay, let's talk about a bit in terms of in powers of 2. So let's say instead of 5, let's talk about 8 bits. So if you have got 8 bits, that would be better for us. If we have got 8 bits, so we will have 1 bit for sign, and then we are left with 10 bits. So we can have any combination we want. Let's go with 4 and 3. So let's say we have got 4 bits for the integer part, and then we are left with just 3 bits for the fractional parts, right? So decimal point is fixed, and that is at this point over here. So for 4 bits, the maximum you can go is have all of these 4 bits as ones, right? And this is the maximum integer part. So this would be 15, right? 1111, because the sign is taken care of by another bit, so we are not interested in sign over here. So 1111 means this could be 15. And if you have got 3 bits, so the maximum fraction that you can go is also 111 over here. Now again, this is very simple because each bit here is a power of 2. So before the decimal, this would be 2 raised to power 0, and it's going to grow in this side, right? And after the decimal, it would be 2 raised to power minus 1, and it will reduce in this direction. So if this is your number where you have all of these as ones, so you can just calculate this, because we know very easily the integer part is going to be 15, and then the fractional part is going to be, so we have a decimal point over here, and this is 2 raised to minus 1, which is 0.5, and then half of that, which is 0.25, and half of that is 0.125. So if you add all of these, this would be something like 0.875. So the highest number that you can store in this format is 18.875, right? Okay, so even with fixed point number system, you're going to see that not all of the real numbers could be stored, because when you're talking about a number line, it has got infinite numbers, right? Even if you are talking about just 2 numbers like 0 and 1, right? So in between these 2 numbers, you have got infinite real numbers. Okay, so you can have any any small part over here as well. Say for example 0.1. So if you talk about 0 and 0.1, again you have got infinite numbers in between these 2 as well. So you cannot store, the first thing that you have to understand is you cannot store all the real numbers, right? So let us just see, this is the maximum that we have. What is the next to that? What is the next number, the number less than this? So if you're talking about number less than this, what should we do? We can just reduce one of the weights from the fractional part. So instead of having a 111 over here, let's have a 110 over here. That is, we are adding just 0.5 and 0.25, that would be 0.75, right? So the next number, the number smaller than this, would be 15.75. So this means that there are a lot of numbers that have been skipped, right? So this is always going to be the case. So you cannot store 15.8 in this format. You cannot store 15.76 in this format accurately, right? So what to do? If you come across a number like this 15.8 and you want to store it in this format, what should you do? You go with a number which is going to give you the least error. Okay, so we go with the number, we go with a representation because these are two valid representations. And 15, if you want to store 15.8, that cannot happen. So we should go with a representation which is going to give us the least error. So if we say 15.875, so the difference between 15.8 and 15.875 is 0.075. If we go with 15.75 and 15.8, the difference here is 0.05, right? So 0.05 is less than 0.075. So this means you are going to select this format, this representation to store, if you're talking about storing the number with the least possible error. So not all the numbers could be stored. So this is the first thing that you have to take care of when you're talking about real numbers. The second thing is you are storing all these numbers which have a difference between them, which is say a constant distance, which has a constant distance. Say for example, the least number here, which is also called as unit of least precision. So we are always going to talk about this ULP over here when we're talking about real numbers. It's called a unit of least precision, and this is the number, or this is the least precision that you have. Precision means that it's in terms of numbers, how accurately can you represent them. This is same as resolution when you're talking about images. So a good resolution means that there are more bits for a particular pixel, so you can represent more pixels. And in ULP here, when you're talking about numbers, so a unit of least precision would be the least power that is going to affect any two representations. So for example, we changed the unit of least precision from 0 to 1, and we saw that there is a difference like this over here. So here the unit of least precision is 2 raised to power minus 3, right? So this is unit of least precision. So you cannot have anything lower than that can be stored over here. And there is always going to be difference of 2 raised to the minus 3 between any two or multiples of 2 raised to the minus 3 between any two representations. So if you're talking about two consecutive numbers, they are going to differ by 2 raised to the minus 3, right? And when you're talking about storing any number which is not possible, then you talk about storing it with an error which is less than unit of least precision divided by 2. So the error should be always less than unit of least precision divided by 2, which in this case, if you divide this by 2, which is as if you have subtracted one more to that, so that would be 2 raised to the power minus 4. And 2 raised to the power minus 4 is, what is 2 raised to the power minus 4? It's 0.0675, right? So 0.125, when you divide that 0.125 further by 2, and it's going to be 0.0675 now. Right, so you can see here, so that the distance between this number and this number was 0.05, which is less than 0.0675. But here this distance is greater than 0.065, so we cannot store it in this format. We have to store it in this format. So I'm going to come to that later when you're talking about floating point numbers. So I'm just having a discussion on real numbers first. So in fixed point, the point is fixed. This is this is a disadvantage over here because you cannot store bigger numbers. So for example, you cannot store more than 15%. So if I need to store something like 1,000 over here, I cannot do that, right? Because this representation has got a fixed point, and you cannot change that. So maybe we don't need such resolution. So maybe we don't need such resolution that there is a number which is having a 0.75 or 0.125 difference between them. Maybe you need something that is bigger than that. So we come with other schemes here. So fixed point has this disadvantage that if you're going with fixed point number systems, then it has got low precision here and range. So basically the main thing is okay, precision is going to be low because it depends on the fractional part that you have. But the range, the main disadvantage here is that the range is very low in this case. Okay, so then we have another system which is called as a rational number system to store real numbers. This is going to be good for you because rational number systems are going to store a number as two integers, right? And their signs as well. So the sign of the whole number. So the thing is going to work well if you have numbers that can be stored in a rational form, right? So not all real numbers can be stored in this way. Can you give me an example? Can you give me an example of a number that cannot be stored in a rational form? There are many examples. Anyone? Okay, okay. First of all, I'll just go through the rational numbers. So if people are uh, not familiar with rational numbers, so if I said that in previously that there is a number like 0.1, and this number cannot be stored accurately in a fixed point number system, right? Because what we had was zero point 0.5, 0.25, and 0.125. So a 0.1 would be, how are you going to store 0.1? So what you can do is have it as something like point. So the closest that you can go, if you have 3 bits for fixed point number system, so if you want to represent 0.1 over here, 0.1 of decimal, sorry, I forgot to mention that. 0.1 of decimal is and we want to store it in the binary format, right? So we want to store that in binary format. So what is this number 0.1? So if in binary format we have a 1 over here, that would be 0.5. So we cannot have a 1 over here. So we need a 0 over here, right? Because that would be too big a number. So we need a 0 over here. So, and then if you have a 1 over here, that would be 0.25. Again, a bigger number than 0.1. So you cannot have a 1 over here as well over here. And if we have just 3 bits, so you're left with just one more bit. So if you have a 1 over here, this number would be 0.125, right? So this number would be 0.125 in decimal. Are you all getting this thing? Okay, so this number is 0.125, and if you talk about the unit of least precision divided by 2, so that would be this difference between these two numbers. So what is the difference between these two numbers? It's actually, the difference is 0.025, which is obviously less than what? 0.0625. So this means that this is the most accurate that you can store, right? So this is the most accurate that you can store 0.1. So but this is not 0.1. So for example, if I have a program in which I need to multiply 0.1 with some number, say 30. So if I want to have something like 30 and I want to multiply it by 0.1, I'm expecting my answer to be what? 3, right? Why isn't anyone giving any input? Yeah, I need answers from you. So I need an answer like 3. But if I'm storing this number as 0.125, what am I going to be expecting here? So that won't be 3. If I multiply this number with the one which I have stored over here, 0.001, this is not going to give me 3, right? So this means that 0.1 cannot be stored in this way. So one way to store 0.1 is, since 0.1 is actually 1 divided by 10, right? So one way to store this is to store it as 2 integers. So we call one of them as P, another one as Q. So P would be the numerator here, which would be 1. Q would be the denominator, which would be 10, right? So your format would be something like a sign bit plus B bits for P and bits for Q. So P and Q are going to be 2 different integers, and because the sign of the number is just one sign, so you need to have something like P and Q can be unsigned numbers, because you don't need P and Q to be signed numbers as well. So you have reserved a bit for sign, and then you can have two integers, and they can be different the numbers that can be stored in this way, like I gave an example of point 0.1, and there can be other examples, but they can be different numbers which still cannot be represented in rational form. Can you give me an example? So I was asking about an example over here.
So the example would be the value of pi.
Pi, right? Good. So pi is a very famous thing, and most of the students are going to give an example. So pi. So pi cannot be represented in a rational form, right? So
Yeah.
and there are other examples. For example, the value of e, right? So the natural number. So again, and there are other examples as well. So not all numbers can be represented in this way, but this is one. This can be one scheme to have numbers stored in two integers, and then you do your arithmetic depending on that. But arithmetic gets a little complicated. um, the arithmetic gets a little complicated if you have numbers stored in rational form. Okay, before I come to floating point, then there is a logarithmic number system. Logarithmic number system don't have a particular standard, and then give me different ways to store a logarithmic natural numbers. So if I give you an example over here, that would be something like we can have different. Um, so in a logarithmic number system, what we have is we have two sign bits here. Uh, one is for the fractional part, one is for the whole number, the other is for the exponent. And then you have your numbers here, and that number again has an integer part and a fractional part, right? The base is implied over here, so it's not stored. The significant part is also implied over here, so it's not stored over here. Um, you can have sorry, if you're going to talk about so there are different ways. So if you're going to talk about a significant part which is fixed, then you don't need an integer value over here, you just need a fractional part and an exponent part, right? So this is actually the integer and fraction are for the exponent, e, right? So and that base is 2. So let me just give you an example here. Um, so if I have something like 2 raised to power 15.5, right? So this 2 is implied, so it's not stored over here, but this I part is stored over here. So this is the integer part, and this is the fractional part, right? And this is the sign of the whole thing, and this is the sign of the exponent. So this is how you can store numbers in logarithmic values, right? So what will this be? So 2 raised to power 15.5 is going to be a very big number, right? So logarithmic numbers are usually used where you are more interested in having bigger numbers, right? Having more ranges. So again, so the integer part and fractional part are for the exponent over here, and the base is implied over here. So it's not stored, and these are the values that can be stored. So this is a way to store real numbers as well, right? So again, you can see here that if you have say I all zeros and fractional part all zeros, then you have 2 raised to power 1, which is going to be what, 2. And yeah, so again there are certain limitations that you can have, but again this is just one way of storing logarithmic number system. And then there is no standard in this case which defines that all logarithmic numbers should be stored in this way, so that there is no standard over here like we have a standard in a floating point number system. So I'm going to come now to the floating point number system, which is our main task in this lecture. Yes, any questions here?
Sir, just I just need to ask that if is there any limit for the bits? Just like you mentioned that 4 bits were reserved for the integer part, and 3 bits were fixed for the in the fixed point. Is there
Yeah,
any limit?
yeah. Obviously, there would be some limits here. So, for example, if I give an example, let's say we have 16 bits for storing logs in number system. So you just need 1 bit for each of their signs. Then you have to decide on your own how many bits do you need for I and the fractional part. So, for example, if you go with equal, so then you have 7 plus 7 over here. So 7 bits for integer of the exponent and 7 bit for the fractional part of that exponent, right? So the main thing is the exponent has a fractional part. We are going to see in floating point number system, exponents are always taken as integers there, but not over here. In logarithm number systems, we have fractional part as well. Now, the advantage of logarithmic number system is that their addition is so that's not the advantage, but advantage here is the multiplication division gets easier. The disadvantage is that the addition and subtraction is complicated, because if you need to add two numbers having different exponent values, how are you going to do that? You need to first of all have their different their exponent same as well. So if you need to add 15 with 14.25, that's going to be tough, right? But if you want to multiply this, that's easy, because you just have to add their exponent, right? So so the multiplication is quite simple over here in this case. So obviously there are going to be some limits to that, how many bits you need to reserve for that. It's not necessary you have equal bits. You can have less bits for integer and more bits for a fractional part. It depends on how you want to how you want to use those logarithmic numbers. Okay, so now I'll come to the floating point number system. Now, in a floating point number system, there are going to be 5 things. And this is the most common scheme, and there is a standard also available how you can store numbers in floating point. That's the IEEE 754 format that we are going to study shortly, inshallah. So first of all, I'm going to come to the things that are required over here. So when we're talking about floating point number system, we have a plus minus s into b raised to power e. Now, as you can see here, that there is a base, there is an exponent which is the power of that particular base, and is multiplied by a significand, right? So this is how you store floating point numbers. Okay, so let me just give you an example first, and then we are going to come to the standard. Um, so as I mentioned here, that it's something like plus minus s into b raised to power e. Okay, so there's one more thing, and e also has uh, a sign, right? So this is your first thing, this is your second thing, this is your third thing, this is your fourth thing, and this is your fifth thing. So there are 5 things that you have to store. Okay. Okay, so can we have some reductions here? So one reduction can happen, that b, if you want to fix this b to 2, because if you're talking about binary number system, so you are talking about always having a power of 2, so you don't need to store that 2 so in that format. So b can be reduced. So instead of storing b, you just have to store the sign of the number, the significant value, the exponent value, and sign of the exponent. When we are going to come to the format, we are going to see that in the IEEE format, that sign is merged with e as a single number. So then we just have 3 things to store in a floating point number. Okay, so what is the advantage of floating point? In when you're talking about floating point, we see here that we can have lower ranges, and as well as we can have higher ranges, and we can have better precisions. So this is the most common scheme. It's called floating point because the decimal point is never fixed at a particular point, and you can have different fractional values, right? So let's come to an example. So this is what we have discussed earlier, fixed point number system. So the disadvantage here is that you cannot have a square of any of these numbers. So if you have two numbers, a very small number and a very large number, neither of them has their square available. If you're talking about floating point number system, which is represented as plus minus significant to base exponent, you're going to see that it has a different way of storing numbers. And normally what happens is that when you are talking about numbers closer to 0, then you're going to see that their precision is higher. As your range increases, you're going to see that they are more sparse. But this is what we needed as well, right? So this is the way when we're talking about fixed point number system, each number has a fixed distance between itself from the previous one. But when talking floating point number system, those numbers have bigger differences as you go on to bigger numbers. So let's start with floating point number system. So as I mentioned, we don't need all of these 5 things to be stored. So if we have the base defined and the exponent having these represented in its signed form, then we just need to store the numbers, the sign of the whole number, and we need to store the significant, and then we need to just store the exponent. So there are just going to be 3 things that we are going to store. Okay, before coming to that, let's take an example here. Let's take an example, and I need your inputs if you want to. Okay, so we have numbers represented in this way. So what we have done is we have said that this can be stored as plus minus s into 2 raised to power, because base is fixed, some number e, and you can have positive e as well as negative e. Okay, so let me I want to store a number like 48.5. Okay, so I need to store a number like 48.5. So this is the decimal number, so I need to convert that first of all in its I'm having a little noise effect over here. Wait a minute. Okay, so there is a little noise over here. Okay, so if I have a number like 48.5 and I need to store that, forget about the base 2. Let's talk about decimal number system 48.5, and let's talk about base 10. So the one way to represent this is 48.5 into 10 raised to power 0. Okay, I cannot draw it very accurately, so let me just try it once more. Into 10 raised to power 0. Okay, so this can be one representation. Okay, second representation could be 4.85 into 10 raised to power 1. Okay, third representation could be 0.485 into 10 raised to power 2. Now, which of them is correct? Is anyone? Which of them is correct? 1, 2, or 3?
So currently, if we take the 0 towards the left hand side, we put minus, I guess, -1, -2, right?
I didn't get your question. You were asking about what?
So I was saying that the points 2 and 3 you wrote, Wouldn't there be 10 to the power minus 1 and minus 2?
No, the thing is, if you're reducing the magnitude, you have to increase the exponent. Okay. So if you're reducing the magnitude of a number, then obviously you have to increase the exponent to make that same. So as Hail Said Heather mentioned in the chat that all of them are correct. So if all of them are correct and he's true that all of them are the same thing, so this means that I can store a single number in multiple ways, right? If I go with this format, for example, plus minus s into 2 raised by e, so this would be my s, this would be my base, this would be my e, and the signs of all of these are plus. So this means that I have different ways to store the same number. Isn't this correct? Do I have different ways? Also, I stopped over here 3. I could have another one, 4 and 5 and 6 and 7, and I can have multiple ways to store the same number. I can also have a number like 485 into 10 raised to power minus 1. That's the same thing as well. Okay. So if I ask you which of these is going to be the correct one, if I ask you which of them is actually going to store 48.5, so what would your answer be? So you are going to be confused. So there is no difference between all of them. So all of them are the same thing. So we have to agree that a number should be represented in just one way. Okay. It's because if a number has got multiple representation, then you are going to lose those representations, because if you have just for 24 bits, if you have got 24 bits to show something, the representations are 2 raised to power 24, right? So if you are having multiple numbers, the same numbers represented in different ways, this means you are going to lose the different representations in useless in the same numbers. So that is a useless thing to do, right? So you need a single representation. So first thing that you have to decide is on one rule, that which of them should go forward. Okay, so if I ask you, what would your answer be? Which of these 3 or 4 do you think is the best one? That seems okay. This is something that is going to be
Still,
applicable.
if it is said that we can store more, or we have more bits for the significant part, so we can go with 48.5, because 48 is there in the significant part, which will require approximately 1, 2, 3, 5 bits for storage. So it actually depends how many bits are we given to store the significant part.
Okay, so Ms. Shirina says that if we have we need to first of all define how many bits do we have for storing the significant part, and then this 48.5 can be stored. My question was, yeah, 48.5 can be stored, and 2 and 3 can also be stored. So that's not a matter that they cannot be stored. So say you have got enough bits to store any of these, even 485 as well. What are you going to choose? So the question is this: that what are you going to choose? What are you going to prefer? Are you going to prefer 0.485 or 4.5? Because there are different ways to store that. Now it's going to be better if we have
Whole
any of these 2 representations. Why? Because in 2, what we have is a single digit before the decimal point, and in 3 we have a 0 before decimal point.
yes.
Both of these representations are acceptable because they make sense. Because if you have got many digits to store, then it's so this is just one example. I can give you different other examples as well. It's going to get very complicated to do that. So for example, if you have to store say 10,000, right? And let's say we say that our standard is that there should be a single digit before the decimal point, right? It shouldn't be 0. There should be a single digit, right? Except 0 before decimal point. Then the only way that you can store is
1
this.
into 10 to the power
Yeah,
minus
you're going to first of all convert this into 1.0, and then you're going to see that you have transferred that decimal point from this place to this place here. So you've reduced the magnitude 4 times, 10 to the power 4 times, so you are going to increase it by 10 to the power 4, right?
Yes.
So this
Yes.
this is going to be the only representation for you storing it. If you say that you need a single digit before the decimal point. So if I have another number here like 1457, and I need to do the same thing over here, that there should be a single representation for storing this number, then again it's an integer, but we are going to talk about that as also a real number. So that is going to be stored as 1.457 into 10 to the power 3,
Yes, sir.
right? So this is going to make sense, right? The other thing that you can do is instead of going with this rule that there should be a single digit, you can go with another rule that there should be always a zero before a single zero before the decimal,
Yes.
right? So that can be another rule. So if you go with the first rule that we had was the second that we said. If you go with the third rule, that would be something like you're going to convert that into 0.1
10 raised to the power
and 10 to
5.
the power 5, right? And the same thing here would be 0.1457,
10 raised to the power 4.
right, in 10 to the power 4. So both of these make sense, right? So you can go with any one of them. When you're talking about binary number systems, so since we have just two bits, 0 and 1, right? So if you go with decimal, you have got 9 digits. So there can be again two rules here. So either you can have a single 1 before the decimal point, that's going to make sense, or you can have a single 0 before the decimal point, that's going to make sense, right? Other than that, if you have got more bits over here, then it's going to be complicated, because if you go for say let's have 2 bits, so then there are many numbers we don't have 2 bits, right? So there are going to be many numbers that cannot be represented. So this is the best way. So when we start with the floating point number system, we see that there wasn't any say particular standard for different companies to store numbers. So what they did was some of them went with this scheme, the others went with this scheme. And then again, there was not a fixed base as well. So some of them had a base of 2, some of them went with the base of 16. Some even went with the base of 10 for floating point number systems, right? So there was a lot of confusion in initial days. So then they came a standard, because obviously there were confusions when you are going to write a program which is converting a number in this way and running on another system which is actually expecting that there should be a 0 before the decimal point, then everything is going to go wrong. So since floating point is selected as the method for storing real numbers in most of the cases, then you need a standard, and standard way that all these companies agree that okay, so this is going to be a standard and we are going to stick to that. So then comes the standard, and that standard is actually the IEEE 754 standard. Okay, so I'm going to come to that in the next slide. So we have discussed about all of this. So we need in a standard like this, in IEEE 754 standard or anywhere any other standard, we need to first of all define what should be our base, how many bits should be reserved for exponent and that and significant. Before coming to the standard, let me just give you an overview of how floating point numbers are going to be stored. So this sign has got a single bit, and that bit would be the leftmost bit, or MSB, right? It's going to be the MSB because when you see in sign magnitude number system or two's complement number system, the MSB is basically going to tell you about the sign of the whole number. So this bit here is actually the sign of the whole number, right? So the sign, actually the sign of the significant, but it's not represented with significant, it is represented as MSB, and the significant is as at a different place. Then comes the exponent part, and then comes the significant part. And there is a reason for that as well, because when you're talking about getting the significant part, you're going to take it from the the rightmost side, and then you're going to take those bits, and that's going to be easier thing to do than going for the exponent part. So this is the way we are going to store that. And then there are two formats. I'm going to come to that later. what are those two different formats, the short format and the long format for storing floating point number system. Let's just go with how we are going to store this. So the sign bit, so what about the sign of the exponent? So when you're talking about exponent, the sign of exponent is uh, actually merged with the exponent value itself, like a 2's complement number system. When you're talking about 2's complement system, the negative values are represented along with that number itself. So the higher the MSB is a negative weight, and then you can store anything, any number, and that you don't need to have a sign bit, separate sign bit for that. So it's actually merged with that. The sign is merged with the exponent. So we have this exponent also having this its own sign, right? The significant sign is over here. So when you're talking about significant, and we go with the scheme that there should be a single one before the decimal point, then this means that all of the numbers will have a one before the decimal point. And when all of the numbers have something common, you don't need to store that thing, right? So let me just emphasize this point over here. So when we say that we go with this scheme where all of the numbers are going to have a single one, then when you're going to store that number, you don't need to store. So for example, if I have a number 1.110, oh sorry, you cannot have a 2 over here, 110. So let's talk about binary number system. And let's say this is our number 2 raised to power, I'm writing the exponent in decimal form, but that's actually going to be stored also in binary form. So let's say this is our number that needs to be stored. Now if you're talking about significant part, and you know that always this is the case, that before the decimal there is a single one, and they cannot be any other digits, so they cannot be a 0 over here. So this means that you are left with storing only this number. So you just need to store 110110, and you just have to forget about this one, because whenever you want to do any arithmetic, what you're going to do is you're going to take this number, bring back that one, and then you have your whole number again. So whenever you're going to do arithmetic, you are going to bring that hidden one. Otherwise, this one is not going to be stored, because this is something which is always going to be there, right? So you cannot have anything bigger than 1 over here. You cannot have anything less than 1 over here. It's always going to be a 1 before the decimal point. So this is what we agreed with. So if this is the case, then you don't need to store that one, and that's just store the fractional part only. So this is only going to be stored, right? Any questions here? Okay. Okay, so then if you go with this scheme, that there is always going to be a 1, right? Then this means that there is a problem. And what problem do we have is, okay, so what is the problem with this scheme? If we say that there is always going to be a 1 over here, and we can store the fractional part, the problem is, how are you going to store 0? So 0 is a very common number, and it's used with, a lot of places. How are you going to store 0? Because you say whatever number you are storing is actually 1 point something, 1 point the fractional part. So how are you going to store 0? So this is your representation now. Okay. So this is a little problem here, that if we say that there was always going to be 1 before the fractional part, before the decimal part, then and fractional part can be anything, and we are going to store the fractional part only. You can have any value of e, but that is not going to make any number 0. So the maximum, if you go with 2 raised to power 0, that's going to be 1. If you go with 2 raised to power minus 1, that's going to be 0.5, and that's going to make this thing reduce. It's going to reduce that, but it's not going to make it 0. So if you go to 2 raised to power minus, so we had 2 raised to power minus 1. So if you go with 2 raised to power minus 2, then it's going to be 2 raised to minus 2 is going to be 0.25. It's going to reduce this thing further, but still it's not going to make it 0. So no power of E can make this thing 0 unless you have what? E as what? Anyone?
Sir, infinity?
Minus infinity. So
Sir,
if you
as an
have,
infinite and
yeah,
infinite
if
infinity.
you have 2 raised by minus infinity mathematically only. So if you're talking about mathematically, the mathematics, then 2 raised by minus infinity is going to give you a very small number, which when multiplied with this number is going to give you 0. So 2 is power minus infinity is always is taken as 0. So then you are going to have a value of 0 in this case. But again, E is a fixed number of bits, so you cannot have infinite E value as well. So this is a problem over here. So this means we cannot store 0 in its actual form, in its actual value form. So what we can do still is go with the same scheme that if the exponent value is a very big negative number, then this thing is going to be a very small number, right? So if I go with the maximum exponent magnitude that I can have and have it as a negative number, like for example, if I can go with 128 and I give this as a negative number, so 2 raised by minus 128 would be a very small number, right? So 2 raised by minus 128 would be a very small number. Still, it's not infinite minus infinity, but it's a very small number. It actually says that you have got 127 zeros and then a 1, right? So you have 0.000000, so you have got 127 zeros and then you have a 1 at the end, right? So it's a very small number. And if you're going to multiply this by 1 point something, it's very good. It's going to be very close to 0, but it's not going to be 0. It's going to be actually 2 raised to the minus 128. So what we can do is assign a representation for 0. So we cannot have an actual representation for 0, but we can assign a representation for 0. Now this graph over here, this timeline over here, sorry. This timeline over here shows the same thing. So sorry, not timeline, this number line. So this is a number line. I always confuse this thing. I call this a timeline. So this is a number line. It shows all the numbers that are possible from 0 to infinity and to minus infinity. So we have got 0 to plus infinity and minus infinity. So all the numbers that are possible, right? So if you're talking about this format, then what you can represent is just this thing and this thing, right? So you cannot have anything other than that. So you can have numbers stored from here till here, right? So it's not very accurate. So but you cannot have this, or neither you can have infinity or minus infinity. So this is the only numbers that you can store. But what you do is you give a representation to plus 0. There is nothing as minus 0, but we are going to come to that because there is a sign bit. So you can also have a minus 0. Sometimes when you're talking about real numbers, minus 0 makes sense because it tells you how you have approached that 0. And then you give another representation to minus infinity and another representation plus infinity. So these three are just representation. They are not going, they cannot be actually calculated from that particular scheme, right? So you have to assign a number format representation. You have to force a representation to be these values, right? So my word is forcing. So we are going to force it, one of the representation to be representing 0 and another to be representing infinity and another to be representing minus infinity, right? Okay, so right, so if you look at this number line, you're going to see that the numbers which are closer to 0 are more dense. That is, you can store these numbers with greater precision, but then the numbers farther away are more sparser and they have a higher range. So that is how you can increase the range, right? So I'm going to come to the format now. Any question up till now? Okay, so we have got two formats, the short format and the long format. Okay, So in both these formats, there's going to be a single bit for sign. That's the MSB. So let me just discuss about short format first. Then there's going to be some bits for exponent, right? And then there are going to be the remaining bits for significant. Okay. So one bit for sign, some bits for exponent, and the remaining bit for significant. Now, when you're talking about short format, there are going to be 8 bits for exponent. When you're talking about long format, there are going to be 11 bits for exponent. And as I mentioned earlier, that exponent is something which is going to store the sign within itself. So let's say we have a 2's complement number system to represent an exponent. That can be one way to store an exponent. So now let's try to store 0. Okay, now let's try to store 0 in our case. Okay, so let's have representation for 0. Now we said that we have 8 bits for exponent in a short format. So we have got 8 bit for exponent. If you go to 2's complement number system and you need the biggest number with the negative sign, so what would that number be for 8 bits? Yes, anyone?
Sorry, would -128?
What did you say? 128?
Minus of 120.
Minus 128, right? So minus 128 would be the biggest number having a negative sign, right? In 8 bits. So what we can say, we say that, okay, so we can reserve this exponent for 0. So we are going to say that 1.0 into 2 raised to power minus 128 is actually 0. So it's actually 0. This is what we are going to say, and we are going to force that this representation it's not 0, but we are going to force that this thing is treated as 0. Okay. Now, if you want to store this thing, what will happen is the sign is positive, so we have got a 0 for the sign. The exponent is 128 minus 128, and 2's complement would be something like 1 0 0 0 0 0 0 because we have got 8 bits. And then we don't store this this 1. We store only the significant fractional part over here. So those would be 23 zeros because they are 23 bits for the significant. So they are going to 23 0. So if you look at this number is actually 0. Okay. Now the problem here is, okay, so this is fine. The problem here is 0 is such a common thing that we need to detect whether this number is 0 or not by a very simple 0 checking circuit. And what we have is an integer. That 0 checking circuit is going to take all the bits stored, and it's going to see if there is a single one, then it says that it's not 0. And this is a very simple circuit. So what they decided in the standard was somehow 0 should have a representation which should have all zeros. So it shouldn't have any 1. So everything is fine except this single 1 over here. Everything is fine except the single 1. And this 1 is because we are going with the 2's complement number system representation. So this means if you need zeros instead of 1s, instead of this 1, all zeros. So this means this minus 128 should be stored as all zeros. Okay. In 2's complement number system, minus 128 is stored as this way, but we need now that minus 128 becomes this. So that's another way, that can be one more way to do that, and that is called as a biased representation. In a biased representation, we add a bias to a number and then store it in its form. So if we add 128 to minus 128, then this means that this number is going to become 0. Now, if we add a bias to anything, we add a bias to all the numbers in that representation, right? So for example, minus 128 we need to make it a 0. So we add a bias value to that, and that makes it 0. So that bias value is going to be stored, is going to be added with all of these numbers. So minus 127 then becomes what? Minus 127 plus 128 would be 1, right? So if you have a 0, now these are the actual numbers, and these are what are going to be stored. So if you have 0, then you're going to add 128 to that, and that would become 128, right? And so on, right? So the maximum number that you can have, because the maximum representation is going to be 255, so you can do it yourself. 255 minus 128 is going to give you 127.
So in tools complement, should we go for one bit less, to the power 7 for 128?
No, my
Because
explanation
I need
is,
how that one minus 128 comes, because it's minus 128 means it's to the power 7.
yeah, it's 2 raised power 7 then, because if you have got 8 bits, we have got 8 bits for storing the exponent. So 8 bits means that you have got 2 raised power 0 to 2 raised power 7,
Okay, fine. We
right?
should start from 0. That's why we are taking to the power
Yeah,
7, and it's
yeah,
equal
yeah,
to
yeah.
128.
Right.
And
And
in tools
this
complement, we are
it,
assigning minus sign.
yeah, this has got a negative weight. This higher weight has got a negative weight, and then you, any number which has a bit and at this place is going to be called as a negative number in two's complement number system. But we are not talking about two's complement number system. We are talking about another encoding scheme, and that scheme is a biased representation. In a biased representation, what happens is the actual number is added with a bias. You can have a bias of anything that you want, and then it's going to be converted into a number like this, right? And you store this number in its form. So 0 will be stored as all 8 zeros, right? So this number minus 128 is now converted into a number which has got 8 zeros, and 127 would be a number which is going to have all 8 ones, right? So this is going to be another scheme. Okay. Now, when you're talking about two's complement number system, we start with 128 to 127. But when you're talking about bias number system, you can have any bias, and then you can have any changes in the number line. So, for example, if you are going to, if you don't need positive, negative values to have equal numbers at each side, then you can have a bias which has got more of positive numbers than negative numbers. So you can always have any bias you want, and that bias is going to change the number of positive and negative numbers. Okay, so but we need to have equal positive negative numbers. I think it's raining here. So
One thing over here is that in previous slide you are taking 0 for both, counting 0 for minus and plus both signs. Why it should be neutralized only for 0? It means 0, and then -1, -2, -3, or +1, +2, +3.
you're talking in this case here.
No. In previous slide, you said that you are taking 0 for both negative and positive and negative for both signs.
Uh,
Here.
yeah,
Plus 0.
I'm going to come to that plus minus 0. I'm going to come to that.
Okay.
Right, I'm going to come to that. In real numbers, it still makes sense to have a
So
negative
it's
0.
rain, because I joined late due to rain. That's why unable to catch
Okay.
it.
So I'll come to plus minus 0. Why there is a minus 0 over here. Okay. So what we are talking about is a short format right now. At the IEEE 750 short format, and we said that there are single sign bit, and then there are 8 bits. Now, when you're talking about 8 bits, then there can be different ways to represent that. So I was on this point that when you're talking about a bias value, you can have different bias values, and a bias value is going to change how many positive and negative numbers you have. So if we go with equal one, we cannot still have equal positive negative numbers. There's always going to be either one positive number bigger, either one positive number more than the negative one, or negative more than the positive one. So when you have 2's complement number system, the range is from 128 to 127. So you're going to see that there are more negative numbers, one more negative number than a positive number. But if you have a biased representation, by changing the bias, you can change that and you can have more positive numbers than negative numbers as well. So if we go with the bias of 127 instead of 128, if we go with the bias of 127, then this means that zero, actually a number zero, which is actually not zero. It was 120 minus 128 in our previous example. But if you need to have it zero and having a bias of 7, we need to have it from 127, and then we can have 255 as 128. So now we have got one more positive number. So this is a little different than 2's complement. You are having 127 to 128, and this is because you have selected a bias of 127 instead of 128. Right? I'm going to repeat this. You can change the number of positive and negative numbers by changing the bias, but that bias is always obviously going to be fixed. But if you need equal numbers, then a bias value can be 128, as we have seen in the previous example, or it can be 127 as well. If you go with 127, again, this is also equal, because in 2's complement there was just one more negative number than a positive number. Here we are going to have one more positive number than negative number. So when we see the IEEE 754 format, we see that it goes with this, actually it goes with a bias value of 127. So there are going to be more positive number than negative numbers in exponent. Okay, so I'm going to come back to that slide. Yeah. So the bias value here is 127, and the bias value is always going to be wait a minute. The bias value is always going to be selected from a formula which is k 2 raised power k minus 1 minus 1. Right? So if k is 8, so this means 2 raised power 7 minus 1 minus 1, that would be how much? 127. Now if you go with long format, there are 11 bits in exponent. So what should be the bias here? 2 raised to power 11 minus 1 minus 1. So 11 minus 1 is 10, 2 raised to power 10 is 1024, minus 1 is 1023. So this here our bias would be 1023. And once we know the bias, what we can do is we know how 0 can be represented, because 0 is actually the negative of this thing, right? So 0 value would be 2 raised to power minus 1023 in this case. And here 0 value is 2 raised to power minus 127. Okay, so this is here representing the different values we can have in the exponent. So this is what I have told you actually. So when we're talking about 0, it has a value of 127, which cannot be given to any other number, right? And infinity is again then the maximum exponent that you can have. Again, this cannot be given to any other number. So plus infinity or minus infinity, it will have an exponent of 128. And this exponent, if you add a bias to it, it's actually going to be 255, all ones, stored as all ones. And 127, again, something which cannot be represented, which cannot be given to any other number but except 0. So 127 is reserved and 128 is reserved. And 126 till 127, these are the usable ranges. Okay, so you can have any number from this range to this range, but 127 is reserved and 128 is reserved for infinity. But this would mean that there could be many representation for infinity. No. If you're going to have an exponent of minus 127, you're going to ensure that the fractional part is always going to be 0. Okay. And if you have an exponent part of 128, you're going to ensure that again the fractional part is 0. So plus infinity would be something like plus infinity, so would be having a sign of 0. Then you're going to ensure that the next, sorry, um, the fractional part, sorry, I made that wrong. um, right, so the fractional part should be, no, the fractional part should be 0, and the exponent part should have all ones. So we are going to have all ones, the 8 ones over here, and then we are going to have all zeros, 23 zeros. So this is going to be a representation for infinity. The main thing is this is all ones because you have selected it as 255, and this is all zeros because you need the fractional part to be 0. Now, then there are other things like, for example, if a number cannot be stored having a single digit before the fractional part, then that is called a subnormal number or denormal number, and which is actually lying in this range. This range over here. These are the ranges which, because as I mentioned earlier, that you can store a number from here to here. But what if a number lies over here, then actually this is such a number which cannot be stored with just with a 1 over here before the decimal point. So if you need an example, so I can give you an example as well. So if say, what for example, we have a number like 1.01 into 2 raised to power minus 126, right? So this is acceptable because 126 minus 126 is within the acceptable range. 127 is not acceptable, but 126 is acceptable, and we have a 1 over here before the decimal. Now, if we need to do an arithmetic on this, and we need to divide this by 2. Now, if we need to divide this by 2, what are you going to get? 1.01 into 2 raised to power minus 127. But we said that 127 is reserved for 0, so you cannot have it as 127. So what you're going to do is you're going to make this as 0.101 into 2 raised to power 126 minus 126. Now, such a number which does not have a 1 before that is going to be called as a denormal number. So this is a denormal number, right? And there are different mathematics for that. So you cannot treat that as a normal number, right? So there are going to be different ways to deal with these numbers, but this is not anymore a normal number in the short format, or single precision as we call that. So it's raining heavily over here in Karachi. Imtiaz Saab? Mohammed Imtiaz, are you there?
Yes, sir. Yes, sir. I'm here.
Are you having rain there as well?
Sir, I'm in 7 on remote area.
Yeah. I'm talking about 7. Are you having rain there as well?
No, sir. Not right now, but there is a chances.
Okay,
Highly
that's
chances
good.
are there.
That's good. That's good. Okay, so I'm going to take a break now.
Fine, sir.
Of 15 minutes. So I'm going to come again to the remaining topics that we have here. So the thing is that we have discussed about the floating point numbers, and this slide here is going to give you the summary of how can we represent numbers in a single precision format. That's a short format. How many bits are there, and how many significant bits are there? What is the range? What is the maximum minimum value
Sir,
you can store?
here rain start is rain start again in my area. I don't know whether if electricity uh, disconnect, I wouldn't be come back again offline.
Okay,
So same here.
that's okay. That's okay. I'm going to continue.
Same
Right?
here.
Yeah, I'm going to continue. But if there is a problem there at your end, so I'll mark you present, right? I'll mark you present.
Thank you, sir.
But I'll continue till the whole thing, so you can check the recording. So all these
Okay,
lectures are
sir.
recorded, so you can check those recordings. But try to be there, because it's better if you have any question and you ask the question at that point. Okay, so this slide and the next one is going to just show the single precision and double precision difference, and what is the maximum minimum range that is acceptable. And then afterwards we are going to come to some question answers after the break, how to convert numbers into an IEEE single precision format as accurately as possible, right? And then we are going to come to the floating point arithmetic later. Okay, so I'm going to take a 15-minute break. So we are going to come till what time is it? It's 25. So we are going to come till 10:40, right? So 7:40, 7:41, right? So let's take a break, short break.